Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this session. We were looking at charge pump PLL with type 2 and order 3 P in the PLL loop. So, let me draw the small signal block diagram of the PLL which we were discussing in the previous session. So, we had this phase error detector PFD whose gain was 1 over 2 pi that goes to a charge pump with up and down signals, and the gain for the charge pump combined with PFD was ICP over 2 pi, and that goes to a loop filter which has RNC1 and a ripple bypass capacitor with C2. In the previous session, we saw the need of the ripple bypass capacitor. The control voltage actually changes the frequency of the oscillator with a gain of kVco over S for the phase. This is the small signal block diagram of the PLL, right. Here you have the input or the reference phase. This is your output phase, right. The phase error can be seen here as phi error. The output of the charge pump is ICP and this node voltage is V control. Okay. The loop gain of this PLL has been ICP over 2 pi, we have seen this before, into 1 plus SRC1 divided by 1 plus SR C1 C2 by C1 plus C2 times kVco over S square into C1 plus C2. Okay. So, for the given loop gain earlier we found that we can have we need to worry about the phase margin for this, and I wrote angle of loop gain as minus 180 degree plus tan inverse of omega by omega z, where omega z is equal to 1 over RC1 minus tan inverse of omega by omega p3, and omega p3 is 1 over RC1 C2 by C1 plus C2. I will just rewrite that again, and phase margin is equal to minus the phase which you are seeing here minus 180 degree, which is tan inverse of omega by omega z minus tan inverse of omega by omega p3, depending on what is the unity gain frequency. So, magnitude of the loop gain with respect to omega in dB happens to be like this. At 0 frequency it changes, and then it at unity gain frequency, and this particular frequency is omega p3. So, let me just extend this line. Okay. So, this is your omega, this frequency is omega u, and this frequency is omega p3, this is your omega c. With respect to this plot, the phase plot happens to be like this, where depending on, so this is going to be minus 180 degree, minus 135, minus 90 degree and minus 45 degree. The phase plot will be like this, okay, and then it will again become minus 135. In this case, the phase margin happens to be this. I showed the other plot also where, let us say, your omega p3 location is something like this. So, you will have a pole omega p3, let us call this as omega p3 dash. You have new omega u dash, and based on your new omega u omega p3, you can have something with the omega p3. It may not actually increase that far, and it will again come back, and this will go to 0. So, the phase margin in the second case is only this much, right. So, the question is now, which of these two plots, how would you like to have the position of omega p3 and omega z such that you get the phase margin which you desire, okay, and which of these plots is a better plot, phase plot to use for your design. When I say better, it refers to which is the most optimum design, right. Now, you take two cases. One case is where the phase plot is actually peaking near the omega u frequency, and let us say this is the phase margin which you want, right. Then, if you think about it, the variation in omega u around this frequency omega u given, right, due to some parameters in the design, the change in the phase margin around this point is actually very less. Whereas, if this is the phase margin which you desire, whether it is low or high, that is another case, but if this is the phase margin which you desire, then a slight change in your unity gain frequency because of your change in a pole frequency and 0 frequency based on your R, C and other parameters, the variation in the phase margin will be lot more. Okay. So, what we need is actually we need a design where we need to design this particular PLL in such a way that the change in the phase margin at the unity gain frequency is much less if you change the unity gain frequency by some amount. Okay. So, this appears to be one of the ideal choice. So, if the unity gain whatever unity gain frequency you want, based on the unity gain frequency, you should place your poles P3 and your 0 in such a way that you get your phase plot variation around the unity gain frequency to be very low. Okay. So, we can do that in a systematic manner. Let us just look at it. So, before I just write that phase margin, let me just write those omega z and omega p3 also, though you know it. This is 1 over r c1 and omega p3 is 1 over r c1 c2 by c1 plus c2. Okay. So, the phase margin, if I make my phase margin to be maximally flat near the unity gain frequency, then the variation in the phase margin with respect to the unity gain frequency will be much lesser around unity gain frequency. So, what I am going to do is I am going to take the derivative of the phase margin with respect to unity gain frequency and make this derivative to go to 0, right. If you do this, taking tan inverse derivative of tan inverse, you will get 1 plus omega u by omega z whole square times 1 by omega z minus 1 by 1 plus omega u by omega p3 whole square times 1 by omega p3. This is equal to 0. You solve all these terms, what you are going to get is omega u square is omega z times omega p3. It is like here your unity gain frequency is a geometric mean of your 0 and the pole frequency. Okay. Now, let us look at it. What does it reflect? That you have omega z. Omega z is 1 over r c 1. I can also write this omega p 3 as omega z times c 1 by c 2 plus 1. Okay. So, this leads to omega z square into 1 plus c 1 by c 2, which implies that omega u is equal to omega z times 1 plus c 1 by c 2. Okay. So, you got the relationship between omega u and omega c in terms of the Kepler ratio c 1 by c 2. So, I am going to substitute this back in the first equation to find our phase, which is tan inverse of under root of 1 plus c 1 by c 2, and the other one is going to be tan inverse of 1 divided by under root of 1 plus c 1 by c 2. So, what you see here is that your phase margin is just a function of the two capacitors which you are choosing. So, in that way I can just take 10 on both the sides and you will solve that equation, which turns out to be c 1 by c 2 is 2 times 10 square of phase margin plus 10 phi m into 1 plus 10 square of phi m. Okay. This Kepler constant I will call this as K c. So, given the phase margin, you can find the ratio of C 1 and C 2. Okay. Once you know the ratio of C 1 and C 2, you can find the other parameters also. Let us look at the design procedure using our phase margin analysis. Okay. So, for a given first you need to know what is the bandwidth and the phase margin of the PLL. So, given omega u and phase margin, how do we know what is omega u and what is phase margin? That you are going to see later. Okay. There will be some other parameters, system level design requirements, where you will get the unity gain bandwidth and your phase margin. So, given omega u and phase margin, you will, because you know phase margin, so you can find out K c. Okay. Tan phase margin into 1 plus tan square of phi. Once you know K c and you know omega u, and because phase margin will give you C 1 by C 2. So, you can find out that omega z is nothing but omega u divided by 1 plus C 1 by C 2. When you know your omega z, you need to choose R. Okay, this is a choice which will be dictated by the noise in the system, but you need to choose R. Then once you know R, your C 1 is equal to 1 by omega z times R. Okay. And C 2 you know is nothing but K C 1 by K c, right. So, you know now you made a choice over R, you know now your C 1 and C 2. Once you know your C 1 and C 2, using the fact that the modulus of loop gain is equal to 1, you can find your ICP as 2 pi C 2 by k VCO into omega u square divided by omega p3 square plus omega u square divided by omega z square plus omega u square. Here you need to know your KVCO. So, you can find the ICP. So, you look at it, given omega u and phase margin, you found your C1 by C2, then omega z, then you choose R, you could find the C1 and C2 and you can find ICP. If all the parameters are chosen in such a way, then you will place your omega z and omega p3 in such a way that your phase margin, whatever phase margin you want, your phase margin plot will always be having a derivative of the phase at the desired point to be equal to 0. Okay. Thank you.